Hello, everyone, and welcome to my presentation on arrival time estimation for unit trains utilizing train matching techniques for the RAS Problem-Solving Competition 2021. My name is Geordie Roscoe, and I will be doing the presentation today. My co-author, Jiaxi Zhao, will not be joining me. First, we'll start with a brief outline here, problem description, going through our data preprocessing methodologies, model development, training, and a complete example for a single train going from North Dakota to Pennsylvania, and then concluding with results and conclusions. Also, just a note on the pictures, these were all taken personally by me and are of trains, unit oil trains, in fact, on the North Dakota to Pennsylvania corridor. However, I looked at the specific dates and none of the trains that I saw are actually in the data set, unfortunately. So for the problem description, our goal is to develop an ETA prediction algorithm for unit trains on US freight railroads using historical sighting and GPS transponder event reports. For our basic predictive model, we're going to estimate only using the railroad reported events. For the enhanced model, we will add the GPS data to improve the quality of ETAs. And as an optional step that we chose not to take, we could have made a cross-OD predictive model where trains that shared partial routes with similar ODs in terms of general location, but not actual track location, could be used to improve the arrival time estimation. We chose not to develop this model because we had concerns about hard to detect differences in the underlying travel time distributions depending on the specific destination and origins, and because we viewed the potential improvement in prediction as very low, given what we saw for the simple single OD pair model. Here's our solution architecture. We'll be coming back to this in many steps. So I'm not going to go through it in full. I will go through it as we step through it. So we will start with our event data processing up in the middle and the top right. So for raw event data processing, we did everything in Python using pandas data frames. First step was, of course, therefore, to import all of our data. Next, we did latitude, longitude correction according to a manually created list. In this case, we only actually corrected one value, which was for Home Valley, Washington, because it had quite literally impossible coordinate values in terms of out of the range of possible latitude, longitude values. Additionally, we did find several other stations to be misplaced. However, we decided not to correct them due to a lack of generality in the procedure for finding them and just a general difficulty in finding those misplaced stations. Next, we did time zone correction using the time zone finder Python library, which gives the appropriate time zone for a given station, given its latitude and longitude. Also added a special case for the CSXT and BNOCT railroad events, which were all marked as Eastern time based on that railroad's reporting policies. Additionally, to validate our procedure on the railroad events for other railroads, we looked at the time zone boundaries for the CN and BNSF railroad events and found that trains did in fact switch time zones at the boundaries given by the time zone finder Python library, which validated our procedure for those events. Now we have filtered our raw data and we want to extract trains. Of course, the easiest thing to do is to simply use the provided train ID field. However, we found several issues with doing this strategy. Firstly, railcars from multiple trains were linked to the same train ID. Additionally, railcars split from a train mid-route sometimes, and not all railcars terminated successfully at their destination. Thus, the individual trip IDs for each railcar associated with the train ID were used to split the raw events by railcar. Note that railcars associated with different train IDs were never linked together using this strategy. Now, this was done to better work with the validation data, where we couldn't really specify what our final result should be corresponding to, and so we really just wanted to stick within the train IDs and match what we believe the final validation will want us to produce. But of course, it would be better to use the process we're going to go through to determine the train ID field directly instead. But of course, we couldn't do that given that we did not have all of the underlying data. With each individual railcar trip separated out, we did some filtering as follows. Firstly, a railcar trip was discarded if the railcar was both loaded and empty at waybill or pull events. Now that deals with railcars in the North Dakota to Pennsylvania corridor that lacked any type of placement event upon arrival and thus also had events for the return trip. This was surprisingly common and really a pretty major issue. and it maybe got rid of about 10% of the data. We realized that discarding was necessary because all we care about, or the main thing we care about, is the actual arrival time at the terminal, which is what we're using for the ETA prediction. But that can only be determined for trains with placement events. If they don't have a placement event, I mean, theoretically, you could do something complicated with GPS events to estimate the actual arrival time. But of course, you can't do that for a railroad event only based model. And there's major issues with expanding that generally and dealing with validation data. And so we chose to simply discard those data points, railcar trips specifically. After that, we looked at the total number of railcars remaining for each train ID and discarded the train ID entirely if there were now less than 30 associated railcar trips. This properly eliminates non-unit trains according to the original provided criteria, all trains needing at least 30 cars, and it also removed empty Pennsylvania to North Dakota cars from the loaded North Dakota to Pennsylvania data, which was kind of a weird occurrence where some cars would not have their waybill event at North Dakota as a loaded event. They were in the loaded data and mapped to a loaded train, but they would have an empty event from Pennsylvania back to North Dakota. And so obviously we don't want to be considering empty trains within our loaded train data. It was good to get rid of those data points. Afterwards, we had to start combining railcars because, again, our goal is to have a single train for each train ID. Adding a railcar to a train involves directly appending all of its GPS events and appending all of its unique railroad events, and of course, incrementing the train length by 1. Now, to be clear, we're only appending the unique railroad events because railroads typically report their railcars as having identical events, except for, of course, having a different asset ID and trip ID. And so realistically, all of the interesting data that we care about is 100% duplicated, and we can get rid of a lot of work by just only doing the unique railroad events. So the process of combining railcars starts as follows. First, we sorted all of the railcars by their first event time. Then we started a train using the GPS and railroad events from the first railcar. And then we iteratively processed the rest of the railcars by adding them to the current train, or i.e. the train with all of railcars above the current point in that sorted list, when their complete set of railroad events were entirely identical, according to the fields of sighting time, location, latitude, longitude, current carrier, and event code, and then making a new train if they are not. As you might have realized, that's a very strict criteria, and so more combination procedures were applied to combine these newly created trains by some more complex procedures that properly map them together even if there was slight differences in the railroad events. We decided they were sufficiently similar. To do this, we first sorted all trains by their first event and last event times, and combined the current and next trains if the number of unique locations for the intermerge of railroad events of both trains was equal to the number of unique locations for both trains. Basically, that's saying, do all trains have at least one perfect match of a railroad event for each of the unique locations? If that was true, there's clearly no long-term deviation between those two trains, and so they were considered to be identical. And the railcars were added together. Next, we calculated the departure and arrival times from each train using the provided methodology, i.e. looking at the waybill and pull events, as well as the constructed placement and actual placement events, and deciding on which event to use for the departure and arrival time. Next, we sorted the trains by those departure and arrival times and combined the current and next trains if all of the following conditions were true. The first event and departure time, are within 60 minutes of each other, and the arrival times are identical, and at least one of the two trains has an identical number of unique locations as for the intermerge of the railroad events. Basically, that means instead of looking at both as we did for the previous procedure, we're ensuring that at least one of the two trains has an identical number of unique locations. And we're supplementing that by making sure the arrival and departure times are sufficiently similar. That allows a little bit more flexibility in missing railroad events for specific railcars. Now, the previous process does not always result in only one train remaining. Thus, we have a couple of more cleanup procedures as follows. First, we sort all the remaining trains in decreasing order by train length, which is equivalent to car count. Next, we set the train ID of the longest train as the original train ID used to separate the data out, and add it to the final data set. And that becomes what we would actually use for validation. And that's kind of this is the true train that should be associated with this train ID. Now, there were a couple cases where next longest train was at least 30 rail cars long, had a different first event time, departure time, and arrival time than that removed train. When that was the case, we essentially said that is a fully valid train that was incorrectly mapped onto that first train ID. So we set its train ID as 10,000 plus the original train ID to avoid any conflicts in the actual train ID field, and added it to the final data set. If any trains remained after that point, we simply printed them out for annual review and discarded them, i.e. not adding them to the final data set. Now, for the provided data sets, we did a full manual review on that output, and that printed output, I should clarify, and no more trains were found that should be put in the final data set. There were several, between 1 and 10 car trains that, clearly should not have been included in the first place and just had, different event arrival and departure times, and seemed to correspond to some small movement in, say, a manifest train. And so obviously should not be in a unit train analysis. And so, yeah, we added no more trains to our final data set. Now, we had a couple things to do with that final data set before we were fully done with it, though. First, the railroad events and GPS events were trimmed according to the train's departure and arrival times, just to get rid of excess events. The railroad events were joined with the GPS events and sorted to get a full list of all events. The origin and destination pair of each train was determined using the first and last railroad event locations. And all trains within each input file were grouped by their OD pairs to aid with the single OD pair based processing and modeling method that will be used later. So now that we've finished all of the event data processing, it's onto the route data processing. The goal of this is to generate station orders and calculate a more accurate distance between stations. Processing tool we used was ArcMap 10.8.1 or ArcGIS, and we had 2 route maps that we used, the USA Railroad Shapefile and the National Railway Network of Canada Shapefile. Those are kind of industry standard tools for railroad location and mapping the rail network. There were 3 steps that we performed. First was importing the data and filtering it. Next was performing the distance calculation within ArcGIS, and finally was generating the final route and station order that could be used by the Python code. For importing and filtering, we determined railroad stations and GPS stations from the events in the route data. Where railroad stations are where there was at least one railroad event at that location, and GPS stations were where events were only reported by GPS transponders and may contain a lot of errors in the location. Next, we of course had to import all of the data, including the rail network base maps and the railroad events and the GPS events according to their latitudes and longitudes. After that, we used the railroad stations to define a target route, modifying any railroad station coordinates based on railroad backward knowledge, and modifying the GPS stations after that deviated from the target route, where we simply removed all of the stations that were off the route. Here's an example of filtering. As you can see on the left, there are a lot of excess stations and a couple stations that clearly just do not belong on the Pennsylvania to North Dakota data set. However, we also filtered out a large section of empty train movements in Missouri and Oklahoma simply because they did not fit with our model in terms of the way trains looped around through there. It substantially screwed up our data processing and distance calculations, and so we really couldn't make good use of them. So after filtering, you see the result on the right. It's substantially more cleaned up, and all of those spurious GPS events are removed. To calculate the route distance, we used an OD matrix cost method in the network analyst tool to calculate the distance along the route between railroad stations and between any GPS station and its prior railroad station on the route. In order to avoid confusion due to parallel tracks or parallel routes, really, the route is divided into multiple sections before calculating the cumulative distance from the origin. For instance, in the example here, if you go to Trenton to Devil's Lake to Fargo, as compared to Trenton directly to Fargo along the KO subdivision, there is a substantial difference in the cumulative distance taken, and that needs to be factored in appropriately. Additionally, you see Jamestown down there, and no trains can get from Devil's Lake to Jamestown. And it's important to represent that appropriately. The way we did that is by splitting that up into sections and then making a network out of it to put into Python Network X. So we divided the route into sections where there was only a single line section. Of course, it could be multiple track main, but basically no major deviations in route length. Found a reference origin station for each of those sections, calculated the relative distance between each railroad station and its reference origin station, and ordered all of the railroad stations from origin to destination. And then lastly, ordered all the GPS stations between pairs of railroad stations and added the GPS station order into the railroad station order. Here you can see sections 1 through 4 for the North Dakota to Philadelphia data, or in this case, actually the Philadelphia to North Dakota data, really a very similar data set. And you can see there's out in Pennsylvania, you have a double track or a 2 segment section where you have 2 routes to get from Philadelphia to Willard. Between Willard and Minneapolis, it's very straightforward, but then it splits into 2 again from Minneapolis to Fargo with the Staples and Wayzata plus Morris subdivisions. And then from Fargo to Trenton and Eland, you can see there's a couple different routes to take, one through Grand Forks and the other straight through Jamestown. And of course, the KO subdivision as the fastest route, cutting straight through the middle. Here's what our output looked like. It's an output list of station order and cumulative distance from the section origin. For the Pennsylvania data, you can see a short 6-mile section of what those GPS events look like. You can see there's a very high density of GPS events in that data. And this is for the data from Philadelphia to Willard through Selkirk. All right, now that we have our route data and event data all processed, we can start performing event matching. And to do that, we're first going to go through a model architecture just to give an overview of how that works. So due to the low number of data points present in our raw data and the high variance in the total travel time for the data points, only relatively simple models and approaches were considered. Primary method of operations of all of our models involves choosing all trains from the historical data with sufficiently quote unquote similar properties as to the target train, where the model defines what similar means in terms of what properties are used and what range of values are acceptable. The remaining travel times of those historical trains from their last reported location, where they match with the target train, and added to the last reported time of the target train to get the final ETA. As compared with, say, base methodology, this procedure does avoid biases of different origins and destinations because we're simply not considering them. The underlying difference in travel time distributions and decide what the trade-off is, what the true trade-off is between those methodologies. For any matching methodology, it is necessary to first define the parameters that will be matched. So for origin estimates, we have very little information. Really, we only have the origination time and the car count. And to avoid directly using future information to predict historical target train behavior, we made sure that all of our year proportion, our week proportion, and our day proportion. A couple examples here of what those proportion values come out to, and we'll go through those in detail. But and was simply used directly as its simple value of car count. For the non-origin estimates, we added 3 more parameters, which are the total traverse time running, and traverse time dwell, definitions as shown there. Combining with the origin estimate parameters, we have a list of 7 train parameters. We did consider more train parameters for similar distance profile between the origin and the target location, but we found that the traverse time values we more detailed parameters and profiles would actually substantially improve results. So for event matching, and this is for all non-origin estimates, because for origin estimates, they all have the same event. The matching is very straightforward. For all non-origin estimates, the last event of the target train must be matched to the closest event for each of the historical trains. Now, last event is different for the railroad event and GPS event models. As such, there is a unique train matching model for each location along the route, specifying that location. Now, since there are relatively few target trains compared to the total number of locations along the route, and since most had different last event stations from each other, a new railroad event and GPS train match model was made and trained for each target train. For the railroad event model, whenever the historical train did not have a direct map, route data was used to find the closest event by distance on each side of the target event, and a new event was made at the target location with sighting time determined using linear interpolation and time, where the target train has its event in red and the historical train has its two events in blue, where you would use the relative distance between the blue and red events and the total time between the blue events to estimate the time that the historical train hit the target train last event location. For the GPS model, things are considerably more difficult, and that's because there's a lot more noise. For the target train, we chose that ending location by incremental event or finding events, 5 events that are within the maximum distance given by reasonable train speeds and further along the route than the last railroad event. That's because you're never going to go backwards, and so having GPS events that occurred before the railroad event, well, there's no added value. They really just say you stayed at that same station, and so you should never go backwards in that way. The events that were found were then averaged in time and distance to get the location of the target train and the time at which the train passes that location. And interpolation factors for each historical train were used for the railroad event model were reused along with the target train GPS location to calculate the matching historical GPS event times. Now, an improved algorithm for this process is absolutely possible through smoothing the complete time distance profile for each train, although the difficulty of doing this is effectively for a generic route is quite high, and so we did not pursue this, although it is definitely an avenue for future research. Summarizing the model type differences, the primary difference is where that target train is reporting as its last location and how that is mapped to the historical trains. As such, the GPS event-based estimates will only be different when the target train has GPS events reported after its last railroad event. Now, this does logically make sense because we're really trusting the railroad events fully, and we should be, because they have consistent reporting locations across trains, and they're not really likely going to be incorrect, at least compared to how consistently randomly incorrect the GPS events are. Now, a segment-based model was not pursued because extrapolating event data to estimate sighting times at locations that were not actually passed is difficult and error-prone, just something you're certainly for different destinations you absolutely have to do, and for different origins, depending on where you're trying to estimate, you still may have to do as well. Additionally, there may be differences in the underlying distribution of train traversal times over that given shared segment, simply based on how often they're going to have constructive placement and where that constructive placement takes place. For the BNSF corridor from North Dakota to Washington, we saw constructive placement occur between 0 and 2 days of constructive placement between maybe 40 and 200 miles outside of the final destination at just kind of random yards, and it seems probable that that is dependent upon the specific destination, and it's affecting the total time taken to traverse a shared segment because that constructive placement is occurring prior to where the cause is, which seemed to be at the terminals in that case. Next, we go on to our train matching models and training. So we'll go through our model structure first. So each model finds matching trains based on a subset of those 7 train parameters that we defined earlier. To simplify calculations and reduce interactions between parameters, each model considers a historical train as matching when all of the specified parameters are within a specified width range around the target train parameters. It's equivalent to essentially using rectangles instead of ellipses for measuring distance, at least for a 2-parameter case. Sequentially, for each parameter, if no trains are found to match fully, we also have the following procedure, where the closest train that is in the range for all previous parameters is considered as matching. That's just kind of a way to ensure we actually have at least one match, no matter what range width values we choose. The model is trained by optimizing the width value for each parameter of the model and to limit the complexity of the models considered and thus the difficulty of training. And because parameters typically only have a small amount of predictive ability, we only consider models with 2 or fewer parameters. Here's an example of what one of those models might look like, where you have parameter 1 on the x-axis, parameter 2 on the y-axis. The target train parameters are, the target train parameter values are in red, that red dot. The red region is given by a parameter 2 width on the vertical axis and a parameter 1 width on the horizontal axis, centered on that red point. And then you have the matching historical trains in green, those 3 dots, and then all of the other non-matching trains are in gray. So in this case, the time remaining for the 3 green trains at the the final location of the red train to get the final estimated time of arrival for that red train. So the final models we considered, we had 13 in total, all of the 1 parameter models, which makes sense given there's 7 total parameters to consider, and all 2 parameter models with the proportion year as the first parameter. And we did that just because we saw proportion year consistently providing the most useful reduction in mean squared error, or the most useful predictive ability. And so we wanted to have some sort of consistency and reduce the total number of models we were looking at from, say, 49 total. For the model training process, the goal is to find the single width value for each parameter in the model that minimizes the mean squared error of arrival time. And we calculated that mean squared error by the following. First, select 1 or more sets of parameter values to test. Those are the width values. And then sequentially select 1 train from the historical data set as a target train while using the rest as data trains. That was done for all of the trains in the historical data set, which is equivalent to a leave one out cross-validation strategy. Next, calculate the squared error of arrival time for each set of parameter values tested for each train in the historical data set, and then average the squared errors for each set of parameter values tested across all the trains in the historical data set. The set of width values corresponding to the MSE is then the result of that process of training. Now, to do that, you need a methodology for choosing sets of parameter values to test. So a brute force search approach was chosen because realistically, we didn't trust gradient descent given the discontinuous and bumpy nature of the optimization surface. Just considering the way the matching algorithm is working, there are lots of discontinuities based on whether a given train is matched. It's kind of a binary decision, and a bunch of binary decisions with a low number of data points is simply not continuous enough for a gradient descent approach to really make sense in this case. And so unfortunately, we had to use brute force search. And we used the parameters on the right to perform that search with, of course, choosing the appropriate values depending on the parameter being optimized for. For each of the 1 parameter models, training occurred directly according to the table. Pretty straightforward, brute force search on all of those values. Now for each of the 2 parameter models, we decided to use the proportion year value taken from the optimal 1 parameter model and just optimize for the second parameter because we needed to save a lot of training time and these models, partially because we're using Python, but also partially because there's a lot of calculations necessary that are required. We really just needed to save training time to have the model train in a reasonable amount of time. And we also saw only a minor decrease in model effectiveness for that. And in fact, many cases, it would in fact use the same proportion year value. And so there was no change in effectiveness. The best fit model was selecting according to the following process to combat potential overfitting issues. So first, all 13 models were trained using the proportion year as the baseline. For the other 12 models, it was selected as better if its MSE was lower than the current lowest MSE. So essentially going through those 12 models, or in this case 13 models, where the proportion year is used as the baseline sequentially. And it was at least MSE basic minus MSE prop year, the minimum of that, and 2,500 seconds quantity squared, lower than MSE prop year, which is that baseline value, where MSE basic is equivalent to MSE prop year, where prop is equal to 1.0, which is also equivalent to the simple average of the train traversal times using the leave one out strategy. All right, now that we have all of our models trained, we can use that with our calculated properties for the data trains and the target trains to produce our final estimations. So, considering only railroad events and then considering all events, the historical train parameters corresponded to the most recently reported location of the target train were used to train the 13 models. The target train parameters, the corresponding parameters of all historical trains, and the best performing model of the 13 were used to choose the subset of historical trains that have sufficiently similar parameters to the target train. And the time remaining until arrival of all the chosen historical trains was averaged and added to the most recently reported location of the target train to get the final arrival time estimate for that target train. Due to issues with GPS event matching, there were several target trains where the chosen railroad event model had a lower MSE than the chosen GPS event model. Now, in all those cases, we decided to just go with the railroad event model for the GPS event model estimate because we didn't really have another choice. Now we're going to go through a brief example of train 593 as a single train example going from North Dakota to Pennsylvania. First, we'll start with event matching. We're going to leave out the route and event data processing because that's the same for all the trains and adequately explained in the paper and hopefully the presentation too. So for all of its filtered events, we have its last railroad event location in Selkirk, New York, which is not shown on here. These are just the GPS events. They're shown as the last 10 reported GPS events. We have colored them based on whether they were too far away in red, green in range of those 5 events that were used for averaging, and gray, which are simply too far away from the last reported event and considered quote unquote too old. Using the station orders, we calculated the distance between Selkirk, New York, and the average GPS location of those 5 stations to be 132.4 miles away. So not too far, but obviously it would be nice to have more consistent railroad event reporting from CSX. So for train 593, we have the following historical train parameters and the railroad event and GPS event models. To clarify, train 593 traveled from Trenton, North Dakota to Philadelphia Eastside, Pennsylvania, which corresponded to 206 historical trains with that same OD pair, which are going to be used for model training and matching, which we'll go through now. So using the brute force search algorithm and that leave one out cross-validation strategy as discussed, we first come up with a simple average where you essentially do the leave one out cross-validation and using all of the trains in the data set that were not the single one being left out. For the railroad event model, the root mean squared error came out to be 44,000 seconds, or approximately half a day, and the GPS event model root mean squared error came out to be 29,000 seconds, or about a third of a day. The best performing railroad event model is found to be the proportion year and traverse time total model, with a root mean squared error improvement of around 3,000 seconds and a proportion year optimal of 0.31 and traverse time total optimal of 60 hours. The best performing GPS event model, on the other hand, was also found to be the same model, proportion year and traverse time total, with a lower improvement in root mean squared error of only 1,400 seconds and a proportion year optimal of very similar 0.32 and a very similar traverse time total optimal of 64 hours. So you can see even though they're using different locations, the GPS and railroad event models actually came up with very similar optimal width values for the parameters. So now with those models computed, we can do our final arrival time estimation, which came out to be February 12, 2018 at 1713 for the railroad event model, same date at 1508 for the GPS event model, with root mean error of 12 hours and 7 hours respectively for the 2 models. And it is important to note that we're trying to do a day before estimate for train 593. And, we're looking at a root mean squared error of around half a day, even though it's supposed to be only a day out, which is really substantial. And additionally, we did a little bit of meta-analysis based on our events and what we believe the procedure for cutting the data was. We indicate that the arrival time is approximately on the next day at 9:30 a.m. So none of our estimates were really that close, unfortunately, which, given the high root mean squared error is kind of to be expected every once in a while, unfortunately. So in conclusion, effectively solving the train arrival time estimation problem with only historical train events is extremely difficult. Much of the variability is caused by unpredictable factors, including train derailments, non-cyclical network congestion, weather severity, and terminal capacity, all of which we found pretty clear indications of in the data in both the Alberta to Illinois corridors and the North Dakota to Washington corridors. Unfortunately, the North Dakota to Pennsylvania corridors, we couldn't really diagnose exactly what was going wrong with our estimates, but it's likely due to that non-cyclical network congestion. Additionally, the models developed were able to achieve a reduction in root mean squared error of approximately 5 to 50% compared with taking a simple average of the time remaining for all trains of the same OD pair. For the example, we were closer to around 5 to 10% range, which unfortunately is potentially just kind of a random variation. And so, perhaps not all of the models are actually truly reducing that root mean squared error and producing a useful estimate, unfortunately. Just goes to show how hard this problem is to solve using the techniques that we developed. Now, we do believe an improved model using machine learning could be developed with changes to the underlying data set would be necessary, however, including using only future data for validation rather than kind of this hybrid where you're using historical data for validation and we tune our model to avoid taking advantage of future data where possible. However, even with all of that work, it's likely that railroad provided time estimates that take congestion into account because they have all that data will still perform better simply due to the substantially larger amount of data that they have driving their models. So here's a quick view of our feedback questions, and we focused on a complete example. I believe we've taken care of that. So please, if you have any questions, thank you for your attention and post them wherever you can reach us. I think in chat is how this is going to work in our virtual session. So thank you very much.